Hi. So now let's think about what's actually going on in the nature. So what we're trying to do is we're trying to mathematically model what's physically happen in the nature. But sometimes what's going on in the nature can be very complex. For example, spread of infectious disease such as COVID-19 or influenza. Another example is the forest fire can be very complex. Motion of a particle under the wind. We studied in the workshop 5 how the motion of a trajectory can be predicted, but we used a numerical solver for that. Another example would be a flow in river network. So it does have the fluid. The fluid motion can be described by the fluid dynamics using the Navier-Stokes equations that we learned last semester with partial derivatives and partial differential equations, which can be even complex to study. Okay. Another example would be the climate system. Okay, so let's assume that once we obtain a model, it became a nonlinear differential equation, or sometimes, depending on the situation, it can be a system of nonlinear differential equations. Okay, but for simplicity, let's assume that this system somehow was a first order system or a first order equation, or we'll learn in the later of the course that higher order systems can be represented as a system of first order differential equations. So let's assume that somehow we come up with a first order system in which can be represented as dx on dt as equals to a function of x and t. Okay, now assume that we would like to study the system starting from an initial point. Okay, starting from an initial point. For example, if I'm throwing a ball in a certain direction, so I know initially where it was and what is the velocity I am giving it to and which angle. Okay, so I know where I'm starting at. And what I want to know is, after some times, what happens to it? Where does it end up? Okay, so we have three different approaches to solve this. The first one is through an analytical solution. That means try to figure out how to solve it. But we have talked for many times that not every differential equation can be solved analytically, especially when they're nonlinear. Okay, if it's linear, then we can use the integration factor method, but not when it is nonlinear. Another option that we have is use a graphical method, such as, okay, so we know the derivative is a function of x and t, so at each x and t values I can draw the slope field. At every single x and t values we can draw the slope field and come up with a slope field diagram and look at how the solution grows, but can be quite complex drawing it, and particularly it can be quite difficult to figuring out a solution curve that go through our initial condition. That can be quite complex and thing to do, or difficult thing to do. And the third option that we have there is use a numerical method. Okay, so using a numerical approach to solve differential equation has been introduced in, I think, in the 18th century. Okay, we'll discuss about it in this lecture. So that's the focus for the lecture. The numerical approximations for the differential equations. Okay, how does it work? We know that the time is a continuous thing that changes. Okay, it's continuous, but when we are numerically doing it, we're going to make a little approximation, or we're going to discretize the time. Okay, So let's say x is a function of t, and which the change of the x can be represented as a first order differential equation. So we know what is the derivative at a given x and t. Okay, and we initially know where it was. Okay, we know initially where it was, and also we know the initial and initial time instance. We can calculate the derivative. So if we go along in that direction, the direction of the slope at the initial point, then after some time t, we can predict the value where the x would have been. Okay, so that's the idea. So we're going to discretize the time axis, and then in discrete time intervals, we're going to iteratively figure out how the solution is progressed over the time, starting from the initial point. Okay. So if we start from here, it goes in this direction, and then calculate the slope at that point, goes this direction and then this direction. Likewise, we can sort of like approximately figure out how would the solution curve progress over the time at this discrete time instances. So that's the basic idea. And then the question now comes to our mind is, okay, we can do that, but what are the factors affecting the accuracy of this approximation? Does this always gives us a very, very accurate result? Or if not, what would be the order of accuracy, and what would be the factors that affecting it? Think about it, okay? So think about that, and in the lecture we'll discuss about two different numerical approaches that people have been developed. Okay, see you during the lecture.